Hello, everyone. So we will talk about now about the states which are countable and which states are uncountable, and then we will give the hierarchy of infinities, how we deal with these. So the best way is to write it and then explain it to you, but we had some complications in the previous video, so I'm gonna read these slides and then we'll talk about the different things in here. Okay, so let's say, so can we compare the size of infinite states in a meaningful way? So we know that the infinite states are natural numbers, integers, rational numbers, real numbers, complex numbers, and then you can get their Cartesian product with and so on. So do you know some way to compare these with each other? So let's say we write, if S is a set of size n, and then let's give S have n elements, then the function from S to this set, which has elements 1 to n, defined by f of S1 is equals to 1, f of S2 is equals to 2, up to f of Sn is equals to n, is a bijection. Thus, we can say that S has size n, this set S has size n, if and only if there is a bijection from the set S to this set, 1 to n. Okay? Now, that's how we can compare the finite sets, and then we can say that how we can say that the finite sets have size, some particular size, if there is a set which has bijection up to the set which contains 1 to n elements. Okay, now let's define these in a more concrete way and say that by a definition, so we have two sets, A and B, are said to be equivalent to each other if there is a bijection from set A to B, and we write this equivalent of A to B in this way, and if A and B are equivalent to each other, so then we can write this symbol between these two sets, and we can prove that the relation we have just defined above is an equivalence relation. And to prove that, what we need to do, we need to show that this relation is reflexive, symmetric, and transitive. And to show that it's a reflexive relation, what you just need to show that A is related to A for any set A. And this is true since the identity function, this identity function IA from set A to A, defined by this, this identity function will always send every element of A to itself. For all A in A is a bijection. Identity functions are always bijections. Symmetric. Now, to show that this relation is symmetric, A is related to B, so we can say that there is a bijection function f A to B. Then the inverse function from B to A is also a bijection. So by this inverse function, we can write that B is also related to A, and this shows the symmetricness of this relation. Now we'll talk about the transitivity. So let's say A is related to B and B is related to C. These two things will give us that there is a function f A to B and there's a function g f g B to C. Then by proposition 19.2, which we have proved in chapter 19, that the composition of two functions is also a bijection. So this composition gives us the relation A to C. So A is related to C. And this shows that the relation is transitive. Hence, in general, this relation is transitive and it is an equivalence relation. Okay, perfect. Now let's give an example. So example 21.1, let's take an example, a set A, which is natural numbers, and let's take a set B, which is set of even numbers, and we can define even numbers like that. Then the function from set A to B defined by f of n is equals to 2n for all n in n is a function which is sending all the natural numbers to the even numbers, is a bijection. Okay. Thus we can say that A is related to B, and which means natural numbers are in an equivalence relation to the even numbers. Perfect. Let's give the another example. So the another example is, suppose A is the set that is equivalent to n. So you can say in general for this statement that A is equivalent to n. This means that there is a bijection function from n to A. Now, for every n in natural numbers, we can define a function, this bijection function, as that it sends every natural number to some an inside A. Since f is onto, we have that A can be written like this. So that means that if there is a bijection from natural numbers to some set A, then we can list the elements of that set. And that is very useful technique to count the number of elements in any set. So we will use this technique to define the countable sets from infinite sets. So let's define the countable sets. So set A is said to be countable if A is equivalent to n. A is equivalent to n. In other words, A is countable if it is an infinite set, all of whose elements can be listed as follows. Okay, so that's the definition for a countable set. Perfect. Now let's understand these more by the example 21.2. So we know that n is obviously itself countable because we can list its elements like this. Now let's take another set. Let's take another set, which is B, which is the set of positive even numbers. And it's also countable because we can also list its elements like this. Perfect. What about Z? Is it countable? The answer is yes. Z is countable, and we can list all the elements of Z is like this. Corresponding, we could define a bijection from natural numbers to Z by saying that we are sending all the even numbers to n, and we are sending all the odd numbers to minus n minus 1 for all n greater than or equal to 1. That's how we say that Z is countable. So you can say Z is countable. Now, the union of any two countable sets is countable. And that's a very nice and useful technique to identify the countable sets. Okay, let's go further and define a proposition which says that every infinite subset of natural numbers is countable. So if you have natural numbers and then you take any infinite subset, like the simplest subsets could be even numbers and odd numbers, then both are countable. So every infinite subset of n is countable. Let's prove that. So to do that, we say that S be an infinite subset of natural numbers. Then let's take a small element s in S. This is the smallest integer. Then let's take S2 in a set S minus the set which contains S1. And then let's take S3 in set S minus the set which contains S1 and S2, and so on. In this way, we list all the elements of set S in ascending order as follows. Therefore, S is countable. You can also define a bijection from this for this thing, which is from natural numbers to this set S, which sends f of 1 to S1, f of 2 to S2, f of 3 to S3, and so on. Okay, so the main concept is if you can list the elements of a set, even though that set is infinite, you can say that set is countable. Or you can define a bijection from natural numbers to that particular infinite set, then you can also say that that set is countable. These are two criteria to say whether the set is countable or not. Let's identify Q as a countable set. So is Q countable? And we will do this by doing this proposition 21.3, which says that the set of rational numbers Q is countable. And to prove this, we need to list the elements inside the Q. And to do that, let's first consider the positive rational numbers. And we show how to list the elements of positive rational numbers. The key is first to write the positive rationals in an array as follows. So imagine we don't have all those arrows inside here, or I can write it for you again. So I'm saying 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, dot dot. Then I have 1 over 2, 2 over 2, 3 over 2, 4 over 2, 5 over 2, dot dot. Then I have 1 over 3, 2 over 3, 3 over 3, 4 over 3, and 5 over 3. And let's say 1 over 4, 2 over 4, 3 over 4, 4 over 4, 5 over 4, and 1 over 5, and 2 over 5, 3 over 5, 4 over 5, 5 over 5, and let's say okay, perfect. Now we can start drawing these arrows from this to this, and then coming back to here. And then from here, 1 over 2 will go to 1 over 3. Okay, and from 1 over 3, we can go to 2 over 2. We can still go to 3 over 1. And from here, we can go to 4 over 1. And let's come back to 3 over 2, and then 2 over 3, and then 1 over 4. Let's go back, go down, 1 over 5, and then go up 2 over 4, 3 over 3, 4 over 2, and then 5 over 1. And this is how we can list the elements. So That's the draw a zigzag line through this array is follows. So I've just explained it to you. And then the list starts like this. So this is the list of elements that we want to talk about. So that's how we list the positive integers. Thus, we obtain a complete list of all positive rationals, showing that Q plus is countable. That's amazing. Now, late, we can write these elements by identifying them as Q1, Q2, Q3, up to so on. Then we can list elements of Q is nothing but we will add negatives in between, and then we will have all the rational numbers in a list. So that's how we list all the rationals, and this says that Q is countable. Perfect. Now, let's say by a proposition that S be an infinite state, and if there is a one function from S to N, then S is countable. Okay. Now, are we losing some, like, are we lowering down some condition? Let's find out. So the image of the function f is the set, which contains all the elements f of s, where s is inside s, and it's a subset of natural numbers. Now we are saying that f is 1. That means f of s is an infinite set. Therefore, by previous proposition 21.2, f of s is countable. Consequently, there is a bijection, which is g, from n to this image of f of a, image of this f. Okay. So now we can regard f as a function from s to f of s. As such, f is onto. F is onto. Why? Because the f of s and s, they are same. So f is onto. So f is onto, f is 1. So f is a bijection from s to f of s. There is therefore an inverse function, which is for f inverse from f of s to s. Finally, consider the composition of this f inverse and g, which will give you a function from n to s. And by proposition 19.c, composition is a bijection. This means that s is countable. So you have taken a set which is infinite, and you just said that it is a 1 function from s to s n, and then s is countable. Okay, perfect. So s is countable. Now, let's do an example and say that find out a more effective way of finding out the sets countable. So let's say q plus is countable. We have done that before. So we can define a function f from q plus to the natural numbers by this rule that we will send every rational number to 2 power m, 3 power n, where m and n are natural numbers and m over n is in its lowest terms. That means you cannot further factor it. Okay, then we say that this function is 1 since f of m over n is equals to f of p over q, then that means that we can write 2 power m into 3 power n equals to 2 power p into 3 power q. This means m is p, n is q. Now, using the fundamental theorem of arithmetic 11.1, we say that q plus is countable by proposition 21.4. So we have just found out a more relaxive way of finding the functions, finding the sets countable. By similar way, we can say that n cross n is countable, and we can define a function from n cross n to natural numbers by the similar way where m and n are integers. Observe again that f is 1, 1, and so on. Similarly, we can also say that n cross n is also countable, since we can define a function g like this from this to this, where it is also 1, 1, and so on. So the main thing is the Cartesian product of any finite number of copies of the natural numbers is again countable. Very good. Now let's talk about the sets which we don't count, which we can't count actually. And those sets are uncountable sets. And are there any uncountable sets? Yes, there are uncountable sets. And that is given by George Cantor in 1874, who says that the set of real numbers is uncountable. And to prove that, we prove it by contradiction. So suppose that R is countable. That means that we can list all the elements of R as follows. Remember that we are doing a contradiction. We are trying to find a contradiction. Okay. So now, if this is true, that we can list all the elements of R like this, then we can express each of Ri's in the list as decimals. So we can define R1 equals to M1 dot A11, A12, A13. R2 is M2 dot A21, A22, A23, and so on up to Rn like this, and so on, where each Mi is an integer and each Aij belongs to this set, which, because you see, after the decimal point, you will always have elements coming from the set 0, 1, 2 up to 9. Yeah. So these AIs can be these elements any number of times, or repeated numbers, or similar number repeating, things like that. Now, let's define a real number R, which has 0 point, B1, B2, B3, and so on. Now, to choose the first decimal digit B1, what we will say? We say that A11 is not 1. So let's say B1 is 1. And if A11 is 1, then let's say B1 is 2. Hence, A11 is not equals to B1. Similarly, A22 is not 1, B1 is 1. And if A22 is 1, B2 is 2, and hence A22 is not 1. And so on up to ANM is not equals to Bn. In this way, we define a real number, this real number, since these are the all real numbers we have written in the list. So since this is the list of all real numbers, and R must belong to this list, because we have defined this R as a real number. So we are saying R should be equals to Rn for some n at least. But the problem is that the elements, the numbers after the decimal point in R, Bn, they are not equals to Nm. So R and Rn differ in their nth decimal digit. Note also that R does not end in recurring nines or zeros. All the BIs are either 1 or 2. Hence, R cannot be equals to Rn, which is a contradiction. Therefore, there is no bijection from N to R, which is to say that R is uncountable. And this is a very nice way of of proving R is uncountable. Now, the consequence of this theorem is so nice. It says that the set of rationals, which is R minus Q, is uncountable. For if irrationals were countable, then we can use the union of rationals and irrationals to say that real numbers are countable, and but irrationals are uncountable. So that's why real numbers are uncountable. If it is, if it were countable, then R would be the union of two countable sets, and hence would be countable. Thus, there is, in some sense, more irrational numbers than there are rationals. Now, in the last, we will talk about a hierarchy of infinities. Now, how we should use these cardinalities of any sets and create a hierarchy of infinities. So we'll give a definition. The definition says we have two sets, and we are saying these sets are equivalent to each other, which is to say that there is a bijection from A to B. We say that A and B have same cardinality, and we write that their cardinality is same if there is a 1 1 function from A to B, and we write that the order of A, or the cardinality of A, is less than or equal to the cardinality of B. And if there is a 1 1 function from A to B, but no bijection from A to B, we write that order of A is less than order of B, and say that A has smaller cardinality than B. I'm confusing the order and the cardinality, but in sets, or in more, like, in some sense they are similar. Okay, perfect. Now, according to this definition, we say that the order of natural numbers and order of the rationals, and even the Cartesian product of naturals cross naturals, is equal. And we can also say that the order of naturals is less than order of reals, or the cardinality of reals. Thus, there are at least two different types of infinities, namely the cardinality of n and the cardinality of reals. Are there more types of infinities? Or is there a set of greater cardinality than reals? The answer is yes again. This is due to Cantor. And Cantor says, if S is a set, and let P of S be the set consisting of all the subsets of this set, if S is finite set of size n, then this power set has size 2 power n. And that's the proposition 17.3. We have proved it, and we have given a wonderful proof of this proposition. You should look at that. Now, we give the hierarchy of infinities in the following proposition 21.5. So let's say S be a set, then there is no bijection from this set S to its power set. Consequently, the cardinality of this set is less than the cardinality of the power set. Now, using the proposition, we obtain a hierarchy of infinities starting at natural numbers. So we say that we say that We say that the cardinality of n is less than the power set of n, the cardinality of the power set of n, and similarly again the power set of the power set of n, and similarly goes on. So thus, there are indeed many types of infinity. And we will end this chapter at this point. So we have learned the concept of countable sets, uncountable sets, and different types of infinities. Thank you so much. Thank you. Bye.